All right, and up next, we will have Jacob Jensen from IPAC, who's going to talk to us about enabling time domain astronomy with RAPID. Yeah, I got it right.
Got it. Thank you. Hi, everyone. Thanks for being here to listen. My name is Jacob Jensen. I'm a staff scientist at IPAC here at Caltech, and I'm a member of the RAPID PIT, which is a project infrastructure team for Roman, who's working hard to try to enable a lot of exciting time domain science for the mission. And so this is a list of our team here. We're entirely located here between the astronomy department in Caltech and IPAC. And we've also had a lot of great contributions from former and current undergraduate students and postdocs as well, so I want to highlight their work too. So I'll be telling you again about the work we're doing to enable time domain science for Roman. So I think for this particular audience, I don't need to spend a ton of time introducing the Roman mission, but of course we know it's NASA's next flagship observatory, which will have a field of view 100 times that of Hubble and be able to survey large regions of the sky even faster. So it's really a wonderful opportunity for time domain science. And of course we know as well, it's launching, sooner than May 2027, which is very exciting. And so it's divided again into 3 core community surveys primarily, 2 of which specifically call out time domain astronomy in their name. So the High Latitude Time Domain Survey, which we heard about from Anya, which will survey high galactic latitude fields, specifically designed to discover transients and do things like 1A supernova cosmology, and also the Galactic Bulge Time Domain Survey, which will be imaging several fields in the Galactic Bulge over several seasons throughout the 5-year mission with high cadence in those fields. But the High Latitude Wide Area Survey as well, which will be taking observations throughout the mission for wide areas of the sky in its different tier, will also obtain repeated passes of the same fields of the sky. So also opportunities there for transient discovery. I want to mention as well the Galactic Plane Survey, which was approved earlier through a survey definition process, which will also include specific fields on some star-forming regions in the galactic plane with repeated observations over some interesting timescales like minutes to weeks. And so this is a very exciting opportunity for galactic time domain astronomy as well. And we all recently learned about the Cycle 1 programs that were approved. So this is just me trying to count quickly, looking through the abstracts. There's probably some that I missed. But there's a lot of exciting analysis programs that are coming up with really exciting ways to analyze all of the survey data that Roman is going to take to do exciting time domain science in a lot of interesting areas. And we heard, again, about one of these programs already yesterday during the discussion, that the Roman Extreme Deep Field will target a single field with Roman's 18 detectors and include 9 epochs over its 3 years to enable some time domain science at very deep extragalactic depths. And I wanted to call out as well this program that was approved to do a survey of Andromeda and the Triangulum Galaxy with Roman, which also includes time domain observations, a few epochs of the entire disk plus high cadence pointings as well. So that's all very exciting. So yeah, how are we going to enable prompt transient discovery and all of this wonderful time domain science with Roman? RAPID is trying to be an answer to that question. So what is RAPID? We are a project infrastructure team for the Roman Space Telescope. And what the project infrastructure teams are designed for is to provide comprehensive and sustained support to the Roman and the science community for research areas that require long-term scientific infrastructure development. So that's sort of our call to action here. And what RAPID is specifically designed to deliver for the Roman community is rapid image differencing, rapid in lowercase letters, not the acronym, image differencing of every new Roman image that has a prior observation where we can do image subtraction. And then we'll put out a prompt public alert stream of all transient and variable candidates with some level of confidence that we discover in those difference images. We'll also provide source match files recording those light curves, which will sort of be appended as we go, and an on-demand force photometry service that runs on our difference images to investigate the photometric histories at any of these observed positions that you might be interested, whether we discovered a transient there or not. So this is just a bit of the structure of our team. Like I mentioned, we're all located here at Caltech. We have a number of scientists working in different areas, from stellar and solar system science out to the extragalactic transients. And I'll mention as well, Ashish Mahabal is leading our work in machine learning and AI. Of course, we're trying to interact with and get feedback from the community as much as we can. So all of our code on GitHub is being developed in public. You can join our Slack, which I'll have a link to later. You can email us, and we had a workshop a couple months ago here at Caltech with the time domain community where we were trying to get feedback as well on our development. We also have an external advisory board who are members of the time domain community, including a representative from one of the Roman alert brokers, to give us direct feedback on our progress as well. And then, of course, we have an excellent team of developers located at IPAC, and I want to highlight two of our most recent members who joined as well just within the last few weeks, Ozzy Bostrom and Emily Everett, who joined our development team. So I'll talk a little bit about, again, the science that we're trying to enable here. In the infrared, specifically for Roman, there's a lot of unique science cases you can probe, specifically in the infrared. One, of course, that gets a lot of attention since the discovery of merging neutron stars and kilonovae is that high opacity from the synthesis of these very heavy elements in our process neutron capture can push the SED of these transients further into the infrared. You can also get cases of transients that form dense clouds around themselves and enshroud themselves in dust. Of course, we have to deal with Milky Way and host galaxy extinction, which Anya brought up already. And as we push to higher and higher redshift, trying to find some of these earliest transients coming from the earliest populations of stars in the universe, we need to move into the infrared as well. And so what this graph is showing you here is just comparing Roman at the top here. In one metric, you might choose to measure time domain potential in, which is volumetric survey speed. So, it's a combination of the field of view and the survey speed of the instrument to cover area on the sky, but also its depth. So, the 3D volume that you're able to probe. And Roman is a pretty spectacular instrument in terms of this particular metric. So I'll just go through quickly again. This is a similar diagram to the one that Anya showed, just showing the mid-infrared, in this case from Spitzer, luminosity of transients, and then sort of their evolution timescales that we've been able to probe with previous infrared missions. So of course we know about things like supernovae, which can form dust or be obscured by dust and have their SEDs peak in the infrared, but also novae, which can have outflows that form dust and have these multi-peaked light curves and contribute to the galactic chemical evolution of the Milky Way, for example. Events like stellar mergers, which can significantly affect the outcomes of stellar evolution and also, the populations of stars that we see. They can actually be quite common in massive star systems, can form a ton of dust in their dense outflows and be really long-lived infrared transients for years to decades. Events like supernova imposters, so these are outbursts from very massive stars that can actually mimic the appearance of supernovae in their luminosities, can also form a ton of dust and be exciting infrared transients. Wolf-Rayet binaries, which are massive hydrogen-poor stars orbiting each other if they have elliptical orbits when their winds collide. As they come close to each other, the shocks formed in those colliding winds can also form dust and produce infrared outbursts. And then, of course, as well, neutron star mergers can give rise to radioactive powered transients like kilonovae, which can also have their SEDs peak in the infrared. So this is just an example of the kilonova associated with GW 170817 detected by Spitzer, several weeks after the discovery of that event. And I want to highlight as well some exciting potential for galactic transients, things like planetary engulfment events for transients similar to stellar mergers, but where the companion, instead of another star, is a planet. And of course, exotic extragalactic transient events like tidal disruption events, where stars are consumed by black holes, which are all very exciting. So I'm running a little short on time, so I'll move through this quickly, but I want to get to what Rapid is actually going to deliver. Our highest priority, of course, is low latency, so we can get alerts out quickly. We'll be receiving level 2 calibrated data from the SOC at Space Telescope, and their requirement is 48 hours from downlink of data to when that calibrated image is available, although I've heard they're testing much faster than this, and it's likely to be something like 8 hours more typically. But then within an hour of receiving that, we'll do difference imaging and put out our public alert stream. We want to make available as well force photometry on our difference imaging and append these source match light curves within 24 hours. And then, on some sort of time scale, maybe monthly or something, all of this will be publicly archived through MAST. And so during early science operations, which is the first 6 months after science operations begin after commissioning, we'll sort of be in a beta stage. So, alerts will be available, use at your own risk, but we plan to stabilize and have everything be sort of verified on that same sort of 6-month early science operations timescale. So this is just a diagram of our pipeline. I won't go into it too much, but we're happy to take feedback on our development. It's all in public on GitHub, so you can check it out, especially if you care about the content of the alert packets. We're definitely looking for feedback there. If there's things you really want in there, definitely give us your feedback there. And so we're leveraging a lot of experience from the development of the ZTF pipeline at IPAC, but of course Roman introduces some important differences. It doesn't have fixed sky grids, for example, and the fields will roll during repeated observations. So I'll just go through quickly again what to expect from us. These are examples of difference imaging that we've been testing with simulations from the SOC of the GBTDS, for example. And then again, we'll produce a public alert stream. So here's sort of a prototype that we made for our conference a few months ago. Now this is evolving quickly again. But we're hoping to include a lot of rich information so that you can make decisions and follow up transients as you like. So of course we'll have machine learning based real bogus to try to weed out false positives. We want to do star galaxy separation on our Roman template images that we'll build, cross matches to other catalogs and data as available. We just heard from Anya, of course, we're going to try to include Roman based photozs in the alert packets as well. If we can, initial light curve classifications as these light curve builds up for any given source. And then in the next talk, you'll hear from Lin Yan as well about the stacking we want to do to get deeper detections of transients with the program called RISE. And then we'll do, have a force photometry service as well. I'll skip this and then just say, I want to highlight some of the machine learning work. Our real bogus initial classifier is published and available now, and we have a summer student who, Ayush Kulur, who has a poster at this session as well on some of the latest improvements and the updates we're doing there. So I'll just leave up all of the ways you can get in touch with us and take any questions. Thank you.
All right. Thanks, Jacob, for the nice talk. Questions for Jacob? All right, I'll start this off. So if people wanted to, what's the best way to access alerts, or what's, for someone who doesn't know anything about it, what's like the entry into studying them or figuring out how to use them?
Yeah, that's a great question. So if you're not familiar with alerts, they're, for example, streaming now from ZTF and Rubin as well. And typically the way your sort of average community member who's interested would interact with them is through a broker. So Rubin has a number of dedicated brokers, some of which are committed or trying very hard to be able to ingest Roman alerts as well. And there'll be a talk tomorrow as well by Ashish on a dedicated broker for Roman called Arandu. And so those brokers are probably the way that you would interact most directly with alerts. But they will be public. You could, learn how and interact directly with the stream yourself if you wanted to as well.
Jessica.
Will you do this for all the surveys, including some of the new gas surveys, with the difference imaging in particular?
Yes, thanks for your question. And the answer is yes. We will do difference imaging at the sort of exposure level 2 single observation level with a stacked reference with any Roman image that's available that has a prior observation to do that difference imaging. Yes.
Okay, maybe one more question. Okay, let's go back there.
Hi. For the real bogus classification, I guess what sort of data are you training on? Mostly like simulated supernova or more variety of transients?
Yes, thanks for your question. So we're training on both, right now, of course, all simulated data. So we have the open universe simulations, which have a set of transients that were included in those extragalactic fields. And then we're also doing our own injections to those images. And we're doing something with domain adversarial training so that we can kind of use one to learn about the other in anticipation of, injecting fake sources into real data and then trying to learn for the real transients, which ones are real. So that's one method. And then we have GBTDS simulations as well. Right now we're working primarily with the ones from Robbie Wilson, Rintimson, which have a set of variable stars in them and our own injections as well, but a very different domain of crowded fields. And then we're injecting sources into the SOC simulations of the GBTDS that I showed as well. So we're trying to train on all of this and do the best we can. Yeah, thanks.
Thank you.
All right, let's thank Jacob again.